Okay, so for Unit 6, Homework 4, let's just start off with question 1. So, baseball is located at the surface of the Earth. Which statement or statements are correct? And there actually is only one of these that is a correct statement. So, as we look through here, hopefully this one was a pretty straightforward question, right? It's basically just another way that they can rephrase asking the same thing, but we know that the force of gravity is always equal and opposite between two different masses, right? No matter whether it's a baseball and a giant Earth, or whatever the two masses may be, we know that the force of gravity is always going to be equal and opposite between those two. So they ask us a variety of different options here, but as long as they're mentioning the gravitational force, I know that the force of gravity is equal and opposite. So option C is the only correct one. The gravitational force on the ball due to the Earth is exactly the same as the gravitational force of the Earth due to the ball, or on the Earth due to the ball. Option D and E, don't be thrown off by those. Those are just saying that the force of gravity depends on both of the masses, right? We already know that it depends on both the masses, so it is not independent then of either one of those. So again, option C, the only correct choice for question. Question 2 here is hopefully also not too terribly difficult, right? If the mass of the Earth and all the objects on it were suddenly to double, but the size remained constant or remained the same, the acceleration due to gravity at the Earth's surface would become what? So really this question is just asking us, how do we find the acceleration due to gravity? We know to find g, right, in terms of my universal measurements, I'm using the universal constant, I'm using the mass of the Earth or the planet, and then the radius of the planet squared, right? So they tell us that the size remained the same, which tells me that r didn't change, but the mass of the Earth and all the objects on it doubled. So really the mass of the Earth here ends up doubling, right? So the only measurement that I changed, g didn't change, the radius didn't change, but I doubled the mass of the Earth. What is that going to do to the acceleration due to gravity? Well, if I double the right-hand side, then the left-hand side is going to double as well, right? So it's going to be 2 times whatever it originally was. So doubling the mass, I double the acceleration due to gravity. Again, hopefully this question is pretty straightforward. As long as you're comfortable with where this equation comes from, it's not a terribly difficult question. Question 3 here does ask us to use several of our new relationships, our new understandings, because it asks us about kinetic energy, potential energy, and mechanical for these two different planets. So we really do want to consider each of those different types of energy, those different energies, and then see how they all relate together. So let's just go ahead and think about it. Planet A has a smaller orbital radius. They both have the same mass, right? So if I was thinking the orbital velocity, which would help me determine the kinetic energy, right? Because I know kinetic energy is 1/2 mv squared. And I know that they have the same mass. So whichever one's moving faster, that one definitely is going to have more kinetic energy, right? So if I think about the two different planets, well, let's think about the orbital velocity. The orbital velocity, we know, going back to our old definition for this, is gm over r. Now that's still true because each of these is following, it does say an orbital radius, and it tells us it's a circular orbit, so we can just go back to the old equation we used to use even going back to last year, right? So if planet A has a smaller radius, what does that do to the velocity? Well, if the denominator is smaller, doesn't that make this fraction bigger, and therefore the velocity would be larger? So planet A has a higher velocity, right? The velocity of planet A is higher than the velocity of planet B, and because again they have the same mass, that tells me that the kinetic energy of planet A is going to be greater than the kinetic energy of planet B, right? So I know that it has more kinetic energy because it's at that shorter, that smaller radius. So if I look at my options, that doesn't really help me a whole lot because A, B, and C all say has more kinetic energy, and then option D doesn't really specify anything about kinetic energy. It just says that they have the same total mechanical energy. So while that is helpful to think about, it doesn't necessarily help me eliminate any of the options. So now let's consider the potential energy, right? And again, this is where it kind of comes into play for us, what we talked about in class in section 6.4. But anyway, when we talk about the gravitational potential energy, right, so whether I call it U or P or whatever I want to refer to that as, I know that that is negative g, the mass of the satellite, the mass of the planet, and then the height above the planet there, right? Once again, the important thing here is the fact that this is a negative quantity, right? Meaning as the radius gets smaller, this number here is going to get smaller as well. Excuse me, as the radius gets bigger, this fraction is going to get smaller, which means it's going to be less negative, which means it's actually a higher potential energy, right? So again, as the radius increases, this quantity would decrease, so it would be less negative, and therefore it would have more potential energy, right? So again, simplifying that, the one that's further out is going to have more potential energy. It's also easy enough if you just kind of think of it in terms of what we're used to, right? If I have a mass that I hold at a height of r, and then I have a mass that I hold at a height of 2r, which one's going to have more potential energy? Well, the one at a higher altitude is going to have more potential energy, right? Because it's going to have more kind of force pulling down on it, more room to fall, all of the above, right? So the potential energy of the higher altitude would be greater, right? So planet A would have less potential energy. So the potential energy of planet A is less than that of planet B. So let's see if that helps us eliminate any choices. So planet A has more potential energy, or excuse me, more kinetic energy, less potential. Okay, so those are both what we saw. Those are true. Option B I can rule out because it says it has more potential. It does not. Planet A does not have more potential. Option C could still be valid though, right? And then again, option D, potentially they might have the same mechanical energy. I don't know yet, right? So far I haven't been able to eliminate very much. So then finally the newest equation that we've seen, right, is how do I find the total mechanical energy for an object in orbit? Well, that's what we saw again in section 6.4, right? In section 6.4 we said that the total mechanical energy is both the kinetic plus the potential energy. But you can actually represent this all as the same measurement. We saw that the kinetic energy ends up being half of the potential. So we end up with a positive g m1 m2 all over 2r, and then a negative from our potential energy, a negative g m1 m2 over r, which gives us a total mechanical energy of negative g m1 m2 all over 2r. Right? So this is the relationship we saw for mechanical energy. Again, it is not given on an equation sheet, so you do have to be pretty comfortable getting there. But it is a very powerful equation for us because the energy, the E over here, represents the total mechanical energy. And from this, it's very clear to see if the satellites have the same mass and the Earth has the same mass, then as the radius increases, once again, this quantity would decrease. But as this quantity decreases, it becomes less negative, right? So if the radius increases, this whole value decreases, which means it has a less negative energy, which means it actually has more energy, right? So again, as the radius increases there, it actually has more energy than before. So then, since as the radius increases, we have more total energy, then planet A, which has a smaller radius, is going to have less mechanical energy. So then as I look back at my options, that takes me back to option A, right? I have less mechanical energy because I have a more negative total energy. So I actually have less mechanical energy for planet A, which has a smaller radius. So option A is the best option here. They definitely do not have the same mechanical energy, and it's not more mechanical energy, even though it can be a little bit misleading at first. Right? We know that if the radius is smaller, yes, this fraction is bigger, but because it's a negative quantity, it becomes more negative, which means it's actually less total energy. So I know that part can be kind of confusing in particular, but hopefully most of this question makes sense. This one, like I said, probably the toughest of the multiple choice questions. If you do have any trouble with this, come find me so I can help you kind of clean it up a little bit more, but option A is the only correct option for us. Question 4 here is really a pretty basic definition of escape velocity or escape speed. So again, the biggest thing is you need to know where that equation comes from. That equation emerges when we know that the kinetic energy needs to be equal and opposite to the potential energy created by the Earth. So again, really all this is saying is 1/2 mv squared would be equal and opposite to the potential energy, which we know is this representation, right? The mass of the satellite ends up not mattering. Whatever is escaping the Earth doesn't matter. Right, so I've got my velocity squared, I've got 1/2, I've got the mass of the planet, the universal constant, and then the radius of the planet. So as I solve for this, I end up getting the velocity equals the square root of 2g, the mass of the planet, and then over the radius of the planet. Once you boil it down to this equation, like I said, hopefully it's a pretty easy solve from here. They tell us a certain planet has an escape speed of v. If another planet has the same size, so the radius didn't change, but twice the mass, how does the escape speed compare? Right. So again, the only measurement I changed here was all of a sudden I doubled the mass, but because I'm doubling that mass underneath the square root, I'm really only increasing this velocity by a factor of the square root of 2 and not by a full 2. So option B is the correct option there. And as you guys can tell, even Maximus gets very excited when we get the correct answer. But anyway, question 4, hopefully not too bad. Again, as long as you're comfortable with the escape speed, it really isn't a tough solve on this one. Okay, so then the last of our multiple choice questions here, right? Because the Earth's orbit is slightly elliptical, the Earth actually gets closer to the Sun during part of the year. When the Earth is closer to the Sun, its orbital speed is, and they're asking us to compare it when it's furthest away from the Sun. Right, again, the easiest way to probably think about this is the fact that the total energy is conserved. Right, so as I'm following my obviously very highly elliptical path based on this picture, but as I'm following my elliptical path, when I get closer to the Sun, my potential energy is going to be lower, which means therefore I have to have more kinetic energy because the total energy of the system is constant. Right, so again, as I'm closer to the Sun, the potential energy goes down, the kinetic energy goes up, which means it's going to be moving faster as it's the closest to the Sun. So when it is closer to the Sun, its orbital speed is greater than when it's further away from the Sun. Right? And again, we talked a little bit about the orbital velocities for this, but I think the easiest approach is just using the fact that energy is conserved, and so as the potential energy decreases, obviously the kinetic energy has to increase. Okay, so question 6, I will try to get all the way through this, but I'll at least set it up for sure and then finish it in the next part if I have to. But they tell us, so we've got the comet traveling in an elliptical path around the Sun. It gets within 8.55 times 10 to the 10th meters at its closest position. Parentheses should have been into there. Its orbital period is 75.6 years, and that is Earth years. And then what is the farthest that it gets away from the Sun? Right. So I sketched the path here. It's an elliptical path. So what they're telling me again is the closest position it gets, they give me that distance of 8.55 times 10 to the 10th. The big concept we have to realize is that would be part of the major axis here. That would be part of the axis, right? So we know that the Sun is at one of the two foci, and then this distance is 8.55 times 10 to the 10th. The furthest distance, right? So what they're asking us to find is this distance here, which would be the remainder of the major axis. It'd be whatever's left. So how can we go about doing this? They give me that distance, obviously. I want to find this one. The easiest way to solve this problem is if we could find the total distance of the major axis, which we defined as 2a, right? The major axis is a length of 2a. If we can find that total distance, then obviously we can just take the total distance minus the 8.55, and that would be the remaining distance, the furthest distance here. So that's really the goal, is we want to find out how long is this 2a, and in order to do that I need to figure out what a is, right? Well, that's where the period comes into play. They give me the period, and obviously they give that to me in years, so I'm going to convert that to seconds. So I will trust that you guys can convert years to seconds. I did use 365.25, so if you got a slightly different number, it's because I used 365 and a quarter. But I end up getting 2,385,754,000 and then 560 seconds. Obviously I took that out quite a few decimal places or quite a few significant figures, but that's just to keep it accurate. So this is my period in terms of seconds, 2 billion and obviously some change. But anyway, that's my period. So then if I want to find A, well, that's just using the period equation we saw, right? That's using Kepler's third law. Kepler's third law showed us the relationship between period and between that semi-major axis. In the equation, obviously, I do hope you guys are comfortable developing this. It is in your notes if you need to go back and look at it. But the relationship then between the period and the semi-major axis is this one, right? It's 4 pi squared a cubed over g times the mass of the Sun. Right? So now it's just a matter of plugging everything in. I should have given you the mass of the Sun on this problem. The mass of the Sun is 1.99 times 10 to the 30th. So that was my mistake. I should have given you that information. But otherwise, you just plug in the rest of the information. Okay, so I will trust that you guys can do that. When I plug in and I solve, I get that A ends up being 2.67 times 10 to the 12th meters. So then 2A would obviously just be twice that, so 5.25-ish, or excuse me, 5.34 times 10 to the 12th. I was reading my answer. And then to find the furthest distance, I just take that minus the 8.55. So my actual answer ends up being 5.25 times 10 to the 12th meters.